Hey guys, Profi Hughes here. As you know, my channel is replete with pendulum videos, and this one will be no different. What happens if you have a pendulum with a certain beat rate and a second pendulum with another beat rate? Where do they meet? That is to say, is this one swinging and this one's swinging at a different rate? Where do they eventually meet as they vary? Well, I'm going to go ahead and show you how to make that happen. Not only am I going to show you where they meet, but in how many seconds each time they'll meet. Again, pendulums are periodic, they're harmonic, they repeat themselves. I know you're used to seeing a pendulum go back and forth, but really it goes in a circle. It requires 2 pi radians. All right? We know that the circle has a diameter, and that diameter will go around 3.14 times. We know that there are 2 radii in one diameter. So obviously, 6.28 radians is the complete journey around the circle. I'm going to go ahead and establish the idea of time in seconds to beat rate. And there's an interesting proof in there. I also frequent a musical site called Authentic Sound. It's run by Wim Winters. But I've been studying pendulums now for about 2 years. Just really got involved in it because he deals in something called whole beat metronome practice. There were 2 ways to read a pendulum. Okay, one is each note gets 1 tick, or that note waits till the pendulum actually completes its period, thereby giving each tick to the subdivision of the note. If you're not musically inclined, don't worry about it. Go out, check his site out, watch his whole series of videos on tempo research, pendulums, and the whole beat metronome practice. So again, I'm going to give you a method for determining when 2 harmonic things, especially pendulums, will meet, and in how many seconds that will occur and then reoccur. All right, enjoy the video. Like, subscribe, share. I don't have merch yet. I don't even have like hundreds of subscribers yet. So anyway, I just have fun making these videos. Sharing stuff with the planet. Enjoy. We'll talk later. Bye. Okay, so here we have 2 pendulums swinging at random, and we'll go ahead and determine how and when they do come together. All right? Okay, so when will this pendulum and that pendulum be in sync? Well, first off, I made a graph of, you can tell the x-axis is the time in seconds, and the y-axis is the beat rate per minute. All right, so I plotted several points, and this is the graph that I came up with. Essentially, if we have a time period of 4 seconds, we have a beat rate of 30. As we divide that by 2, we're going to go ahead and have a time period of 2 seconds. But you'll notice that the beat rate doubles. All right, so that's kind of interesting. It's kind of a proof for whole beat in that a pendulum or metronome that beats 60 actually has a time period of 2 seconds. So your pendulums beating at 60 are in fact 2 seconds. Anyway, we'll go on and divide that 2 seconds in half again. 2 divided by 2 is 1. And we're going to notice that the beat rate doubled again from 60 to 120. So essentially above there I have t divided by 2 equals 2 of the beat rate. So every time I divide the time, I wind up doubling the beat rate. So when t equals 1, b equals 120, then t equals 2, b equals 60. We're going to come up with a general rule about that. All right, so the time in seconds is proportional to 1 over the beat rate in minutes. So in order to make an equation, we need a constant. So I'm going to set the time in seconds equal to the constant of 1 over the beat rate in minutes. And we're going to go ahead and set t equal to 1, and I'll set the beat rate to what it would be, or 120. Solving for k gives us 120. Now we have an equation we can work with. T, time in seconds, equals 120 over b, beat rate in minutes. And if we go ahead and multiply both sides by b, divide by t, we come up with the beat rate in minutes equaling 120 over the time period in seconds. All right, now that we have those two formulas down, let's take a look at the pendulum of the clock on the left side. I did some calculations, timed it, and it came out to 0.8 seconds. That's our t value. The pendulum on my little metronome there, my pendulum metronome, is exactly 1 second as the time period. So what we're going to do is we know that the time period is equal to 120 over the beat rate. So I'm going to set, like you see here, both time periods 120 over the beat rate. And then I'm going to go ahead and change the formula back around to beat rate. And we're going to go ahead and replace the time values for each. Remember, the clock pendulum was 0.8 and the metronome pendulum was 1. Now that gives us a beat rate of 150 for the clock and 120 for the pendulum of the metronome. Let's go ahead and put that back in to our time period, which essentially is now fractional. All I've done is I've taken the time period of 120 over the beat rate, okay? Now we have our time periods in fraction values. So now I have 120 over 150 and then 120 over 120. Reducing the fractions gives my pendulum of the clock 4 over 5 and my metronome pendulum 1 over 1. So now I have the two fractions 4/5 and essentially 1 over 1. I'm going to get the reciprocal of that top pendulum. The faster pendulum, we're going to take the reciprocal. Then we're going to go ahead and juxtapose them. We're going to multiply them together and come up with a number, which is going to be the ratio of the faster pendulum over the slower pendulum. So every 5 beats of the clock will equal 4 beats of my metronome. Let's go ahead and review that. 5 beats for the clock, 4 beats for the metronome. And to check when these will repeat, all you have to do is multiply by the respective time t values. So 5 times 0.8 and 4 times 1 goes ahead and gives us 4 seconds. Those must match. If they don't, you have to do it over again. They will eventually match, all right? It may be a humongous number, but they will match. All right, so we have now the clock pendulum beating 5 times and repeating every 4 seconds, and the metronome pendulum beating 4 times, repeating every 4 seconds. So every 4 seconds, wherever those pendulums started from, they will return. So just let's review. First, find the T and the B, all right? Second, place 120 in the numerator, place the B in the denominator. Reduce both fractions. Best to not use decimals. They get really weird and squiggly and you need a calculator, and actually as you get out into the 10s and 20s you will have some weird numbers. Keep everything fractional. If you don't know how to add, subtract, or multiply or reduce fractions, that's kind of a prerequisite. All right, so 5, take the number of the faster pendulum, go ahead and take its inverse. That just means flip it. Flip the numerator and the denominator. 7, go ahead and juxtapose those fractions, multiply them together. That means that 8, the upper number, will be the faster pendulum. And what you want to do is multiply each by its own t in seconds for the repeat period. And that repeat period must match. So let's go ahead and take a look at the video again, and I'm going to go ahead and show you the 4 seconds, and we're going to just watch them meet. All right? Okay, there. They just met. Boom. Right there, they met again. Outstanding. Like, subscribe, share, and we'll go ahead and make some more videos. And glad you could learn a little something about harmonic motion today. Take care. Bye.